Hello, welcome everyone. So we will be going through our last module, the module number 4 for this particular topic of hydrogen energy from biomass and the coal. So in the past 3 modules we have looked into the biomass, different technologies like pyrolysis and the gasification process, how to get the or maximize the hydrogen yield through that using hydrogen in the biomass as well as in the through the steam as a reactant which reacts with carbon. So, using carbon in the biomass as well as the hydrogen present in the biomass to give you hydrogen. Now, we will discuss about the coal. So, when we look into the coal, first we have to identify or understand the fact that the coal is coming from your biomass. So, biomass is what has given us the coal. So, if we look into the time, as we all know that there was a era called Carboniferous period which is actually attributed to bulk of the coal that we have now. And the reason being there is a very interesting story about that. Is that coal that has come through all the era or whatever plants are today what we have, will it give us the coal after millions of years to the future generation? So, this is a very interesting story, and I have given these 2 links. I would request all of you to go through these 2 links. It is a very interesting story, that it was the lignin, it is the lignin which has given us the majority of the coal that we have. So, in the early era of the evolution, most of the plants were, means not most of the plant, but all the life evolved initially into the under the sea. Then from the sea it came to the ground, but in the sea there was a unique thing that even if the plant grows tall like this tree, if it grows tall, there will be a buoyancy force of the water that will keep it floated, it will not fall under its own weight. But when the plants start growing on the land, then the issue of how the tall trees can support itself. So, there was a millions of years the plant did not have this compound called lignin. So, and this is what you see, the shrubs, the grasses and all, which are very light in weight, which will grow, if they grow tall, they will just bend down and will reach to a particular height only. But to compete, especially in the thick forest, to compete with the sunlight, you have to grow tall, and that is how the evolution happened. But after millions of years, the evolution gave this magic chemical, that is the lignin. So, this organic compound that is giving the strength and the structural stability to the plants and the trees. So, even it will grow, it will not bend under the tree, and even for the smaller plants or the shrubs, it gives the structural stability to withstand the heavy wind or the animals or any impact as such. So, this lignin become a very universal for most of the big plants and trees and all. But there was a problem that still no microbes to decompose, and that issue is still there, but not 100%. Just to imagine, just to give you a perspective, all of you would have noticed, just imagine a coconut shell or a big tree trunk somewhere lying in the open. If you have dry leaves or fruit and all, if you see it in the open, it will be just few days, a week or a month, and it will completely get decomposed, or some insect will come and eat it, or microbes will decompose it completely to the sort of powder. But a coconut shell, if you throw it in the open, you come back next year, that coconut shell still it will be there. You come after 2 years, you may still see it there. You will not see any animal which will eat it because they do not digest. You can't digest the coconut shell, it is very high in lignin. Very high in lignin, we do not have enzymes which can digest the lignin thing. Same thing is with the microbes. Majority of the microbes do not have any enzyme which can digest or decompose this lignin thing. So, it went again millions of years because evolution process is slow. It took again a million of years until a fungus which was found or which was evolved, which could digest, which could attack lignin and can digest it and decompose it. But this fungus came millions of years later, and now right now also you can imagine, if you are in dry places, this fungus which needs high humidity to grow, you will not see this, but if you are in a very wet area or during the monsoon, then only you will see the fungus grows, and it grows anywhere, even on your wooden table, in a wooden shelf, it will grow because it can eat lignin, it can digest it, it can survive on that. And most of the mushroom, it grows on the tree trunk. So, these are some of the evolution process which took some millions of years, and that million of years is called the Carboniferous period. And in this Carboniferous period, when the trees after their life they were dying out, every tree will have its own life, every plant will have its own life. Most of the other body parts except the lignin part, except the trunk, the branches, everything will get decomposed by microbes, animals, insects, they will eat it up. But this lignin based trunk, the branches, they still remained unconverted and they just piled up over in the jungle. And it was not few years, it was millions of years. It was millions of years where it has covered the jungles, in the forest, with a pile of lignin, and then through earthquake or through flood or through something, it undergoes under the ground, and then under the ground within the 1000 years it will decompose slowly, but this is thermal decomposition now. So, in the lignin if you give heat, it can undergo pyrolysis, a decomposition will happen. But there also lignin is much more stable compared to cellulose, hemicellulose, which also makes the bulk of your plant. So, this peat and then further heat and pressure, high amount of pressure. So, it has heat plus pressure, that is moves more under the ground, high amount of pressure, high amount of heat, it converted it to lignite and the coal finally. So, these are typically many people they identify, in some literature you will still find this lignite and peat classified as different category of coal, but we do not need to go under that thing. But the thing is, quality of the coal varies, and how is the quality of the coal is varying is, if we look into the fresh biomass which will have around 55 to 65 grams of hydrogen per kg of biomass, it has around 50% of oxygen in its molecular form. All organic molecules will have 50% of oxygen by weight and roughly around 40% of carbon by weight, and little bit amount of hydrogen and some other inorganics like iron, sodium, chlorine and all, it will be there, potassium and all. It has a calorific value of around 14 to 17 megajoule per kg. Now, when we look into the peat which has come after that, it stayed inside the earth crust for around 10 to 15,000 years. It is a long period, but still you have some 60% of organic matter still left. So, that is you can see how slow the process was and how slow the process is of the coal formation from the biomass. So, still after 10 to 15,000 years 60% organic mass is there, there is a very small increment in the calorific value. Then after 6 crores years or 60 million years, after 60 million years what you get is a lignite which now has high amount of carbon and lot of oxygen has gone out as a moisture, because it will be oxygen will be embedded in that. The dry carbon and the coal will have, or the dry coal will have less amount of oxygen in it. The calorific value also almost doubles. If you look into 14 to 17 megajoule in biomass, and you have almost double the calorific value now. Then again few more crore of years or more than 100 to 300 million years. Now what you have got, the carbon content has now increased to 60 to 80%. The decomposition is happening, hydrogen and oxygen is leaving the system, hydrogen and oxygen is leaving the system. Now you have no organic molecules left, but just see the time scale, 10 to 30 crore years, 100 to 300 million years, that has been the time scale when the trace of the organic compound has left still, and the calorific value also improves in that. And the anthracite, which is like one of the best quality of the coal, that you will get around 35 crore or 350 million years old, which has 80 to 95% of coal, negligible amount of moisture, very high calorific value of this thing, but hydrogen content is very low, only around 20 grams hydrogen per kg of per kg of coal. Sorry. Yeah, so hydrogen content is very low, around 20 gram per kg of coal only. So that is the overall evolution of your coal from the biomass. So that is why I kept these two together. Now we understand what the biomass and how much is the biomass having hydrogen, and then in the through the this long duration of period and under the intense temperature and pressure inside the earth crust, then your biomass has converted to your coal of different categories under the different timeline of the period, and every type of coal will have different content of your hydrogen, but anthracite or bituminous will have very less amount of hydrogen in it. Now this is some of the figures, that is the first peat decay of the vegetative material, second stage is the lignite, third stage the bituminous coal. This you can see like a blackish which looks like coal, and anthracite coal considered by some type of metamorphic rock. So in the literature you will see the different definition of this coal, but this is more having high amount of carbon in it, hydrogen is very low in it. Most of the hydrogen has been lost during the coal formation. So now looking into the coal gasification. So this gasification overall chemistry is similar to what we have seen in the biomass gasification process. It is the early 19th century technology. Coal gas was used to light up the streets in many European cities. So that is coal gas, and this is nothing but your carbon monoxide plus hydrogen. So this was used to light up streets. So that was a street light system in the 19th century. So you can just imagine how old and what could have been. The gas which is carrying carbon monoxide in it is used for the street lighting. Interesting, is not it? Now looking into the quality of the product gas depends on the quality of the coal used. If the coal has high amount of hydrogen, it will have a little higher amount of hydrogen, even though coal gasification, it is the inherently the steam gasification. But if the coal also is of poor quality, it will have high hydrogen, it will have high amount of hydrogen compared to high quality high grade coal will have less amount of hydrogen in your gas or the synthetic gas. So steam gasification and two stage gasification plus shift reaction is used to enhance the hydrogen yield. So this is the hydrogen yield, again the shift reactor that we have seen the reaction of carbon monoxide plus H2O that gives you H2 plus CO2. So to enhance the, and this is the second stage or the what we say the catalytic conversion state which is used for the coal gasification process for hydrogen yield. Now hydrogen production through coal gasification. So coal is gasified first, followed by the products gas passed through catalytic shift reactor with steam supply. Partial oxygen supply helps in exothermic oxidation and hence sustaining the overall process. So this is similar. In the biomass gasification we have seen it is the volatile which was the gas reacting with oxygen, and the exothermic reactions of volatile combustion was sustaining the endothermic reduction as well as endothermic pyrolysis and the drying process. But here the solid fuel, that is the carbon itself, is undergoing oxidation. Yeah, the reaction rates will be slow, but if the temperature is maintained high, if you design a reactor in such a way, reduce the size of the coal particles to very small, you can get a very high reaction rates here as well, and that is what is done typically the pulverized coal is what is used in the coal gasification systems. Very small micron size of coal particles are used, which enhances the surface area, and that is how it enhances the oxidation process of the coal for this exothermic reaction, which has sustained the overall process. So, again the same Woodward process, which is endothermic C plus CO2, and the water gas shift reaction CO plus H2, which is also mildly exothermic process, which is prominently sort of present here. We are not looking into hydrogen based reaction because hydrogen is not much into the system as such. So, this system, and then this carbon monoxide can be used through shift reaction to enhance the oxidation process, hydrogen content. And this is the carbon monoxide, which can be used for further second stage with the separate shift reactor, where we can have the hydrogen plus CO2 giving you high amount of hydrogen plus CO2, and then to get the more amount of hydrogen through it. So, this is the simple chemistry. Unlike biomass gasification reactor, here the shift reaction is preferred to be in the separate second stage as such. Now, looking into the coal gasification process. So, coal gasification process is one of the higher amount of hydrogen, around 25 to 30%, 30% of hydrogen global hydrogen is coming through coal gasification. And you can imagine there is a huge demand, and then there is a huge requirement, a big plants and all. This is one of the very simple, means not very simple, complex, but very economical design. You use the underground or the earth itself as a side for the supporting the reactor. So, here you can see this is your earth, inside it they have dig up the reactor part and they had made the reactor inside. The coal is supplied from here, you have a oxygen separation plant, oxygen is separated from the air and is supplied here, and then you get the gas from it and you sustain the overall process. So, overall the very big reactor you can make it inside the earth itself. So, this is the very popular coal gasification system, and it is pulverized. So, the typically the coal particle size is of the 50 to 100 micron, and typically the reactor type is pulverized coal in entrained flow or fluidized bed reactor. So, these are not preferred much into the fixed bed reactor like the earlier gasification, that example that we have seen in the figure, that was the fixed bed packed bed reactor where bigger size of the biomass was used, but here the smaller very fine size of particles are used because you have to enhance the solid gas reaction, and that can be enhanced by increasing the surface area of the coal particles, and that is done by pulverizing it, pulverized coal, and the entrained flow or the fluidized bed reactors are preferred here. So, in the hydrogen production system what you have is you have a crushed coal, that is pulverization happens here, you put it in the micron level size and the ash comes out, the solid, whatever the gas comes out you remove the particulate matter, that is still some dust, some ash will be flowing with it, the solid particles you remove here. Then you have a special requirement of sulfur removal. Typically in biomass, most of the biomass you will not have much of a sulfur, that is problematic enough to remove it, but in the coal the sulfur content is significantly high, and this needs to be removed before you push it into the hydrogen separator, because those reactor and also this water gas shift reactor, the catalyst used gets poisoned because of the sulfur present. So, that is how you need to remove the sulfur. So, there is a sulfur remover unit, and after that you remove the Cu2 and H2O. H2O easily gets removed by reducing the temperature below 100 degrees by condensation. CO2 is removed typically by amine solution or by high pressure water spray, and then this particular carbon monoxide or hydrogen you can use for different chemicals or the fuels, we have talked about, for example, the FT synthesis which will give you petrol or diesel. But if you are looking for hydrogen, then you have to go through a second stage reactor, that is a water gas shift reactor, because it is the catalytic reactor for high sort of amount of hydrogen to be produced. It can't be clubbed here where there will be lot of sulfur present. In this particular reactor it will not be there. We need to remove the sulfur first and then feed it into the shift reactor, and then by enhancing the hydrogen we get more hydrogen. So, this figure is talking about the fuel cell, but we can use the hydrogen for any purpose after separating it from the system. So, this is how the thing is there. One of the very interesting sort of philosophy or the new thing that is getting prominence in research in India as well is the underground coal gasification. So, let me just spend few minutes here, quite an interesting thing. This is not again new technology, Russians have mastered almost 50-60 years back. So, what exactly it is, like we have seen here in this particular reactor, you design a reactor underground, but in the underground coal gasification what you are doing, you are using the mine itself as a reactor. Here what we have done is we have mined the coal and supplied here. This is coming from the mines, we supply it here, we pulverize it, we do the processing, transport, everything we do, and then we push it into the reactor. We are just saving on the cost of the construction of the reactor. But here what philosophy is, once you start getting this coal out of the cavities, you still have empty cavities in it, empty cavities. Why not use these cavities itself as a reactor? So, these cavities are itself of the coal which has high surface area because it is a huge mines. All the surface exposed will be able to give you a reaction site. So, all these things are here, and in this cavity what you are doing is you have an injection well. Through injection well you push high temperature steam, and then high temperature steam as well as some amount of oxygen, and then you push into this cavity. Here it will react and it will give you, in the production well you extract it up where you get carbon monoxide and hydrogen from the system, and then after that you do the gas cleaning. Because of the reactor everything, you have got the gas cleaning, then pass it through sulfur removal, then water gas shift reactor, enhance the hydrogen content through it, or whatever you want to do it, but the overall reactor is underground. So, this whole huge cavities, it will not be just big like a building, it will be kilometers long. So, these are the sort of a huge reaction sites that you can enhance once you can have a control over it. But yeah, it is not as easy as it looks, because with the reaction and all this, some of the walls it start collapsing and you need to have a control over that. Russians mastered it long back, but it is not a open technology from that. Still I think 1 or 2 underground coal gasification mines are still operational in old part of Russia. I think before the USSR it's in I think Kazakhstan or Uzbekistan. But right now China is also investing a lot in this particular technology, and here this carbon monoxide and hydrogen you can put it through and put up a methanol plant, from it. Methanol, the major feedstock is carbon monoxide and hydrogen, and then you can get methanol through a catalytic conversion process. So, they are doing the carbon coal to methanol projects. China is doing that, and then India is also looking for that. The reason being, reserve of coal and the energy independence. So, you do not know, you never know, like even in the current time or maybe a couple of months back we have seen the Russia and Ukraine conflict. You never know when the energy supply through natural gas or the petroleum will get interrupted. Every country, every sovereign country looks into energy independence, so that we have enough of all type of energy requirement we can fulfill at our own. So, here in India we have a huge coal reserve, but our coal, one of the problem is our coal is not of a very good quality for the use in steel industry or the thermal power plant, because of which the thermal power plant it is used, but the quality is bad. It has very high amount of ash, it can't be used for steel production and all, which requires a high percentage of carbon in it. So, but these are very good for your gasification process. In gasification process, once you master underground coal gasification, a huge big plant running continuously for the years at a very low operational cost can give you a upper hand over getting the synthetic gas or the syngas. Then you can convert it to liquid fuels, methanol, liquid fuels, get hydrogen out of it and use that hydrogen. So, energy independence is one of the things, and underground coal gasification, a cost effective gasification process can be one of the key for it. So, with this I just like to conclude this overall module, and I hope all of you have understood and appreciated the role of biomass and coal for the hydrogen production, the different process and the chemistry behind it. And yeah, just with a thought, there is no better way to sequester carbon than preserving nature. Even if we are using biomass, let us use the agriculture waste or the municipal waste, whatever the carbon is coming through the waste, let us react with steam and produce hydrogen from it. So, with that note, I would like to thank for taking up this course and going through this set of lectures. Thank you.